Hello my friends and welcome back to the Today Machine channel. At the Mapleton Caterpillar facility in Illinois, they specialize in the casting process for engine blocks, a method that combines ancient techniques with modern technology to produce components of exceptional strength and quality. The process begins with creating molds from specially selected sand, known for its ideal size and shape to ensure the best possible engine blocks. This sand is mixed with a two-part resin, which acts as a binder, holding the sand grains together as the mixture hardens into a solid form. These hardened sand molds, or cores, are then coated to prevent the molten iron from damaging the core's interior during the casting process. Once the cores are ready, they are assembled into molds that resemble a stacked sandwich. This flexible assembly process allows Caterpillar to produce engine blocks for different cylinder configurations, including 8, 12, 16, and 20 cylinders, using the same core components. The next step involves pouring molten iron into these molds. Caterpillar's Mapleton facility melts recycled steel and iron, along with added elements like carbon, silicon, and chromium, to create a high-strength gray iron mixture. This molten material, heated to approximately 2,700 degrees Fahrenheit, is carefully poured into the molds at around 2,600 degrees Fahrenheit. The pouring process is precisely timed to ensure the iron fills the mold evenly and solidifies correctly. After the iron cools and solidifies, the casting is removed from the mold, and any remaining sand is blasted away using steel pebbles in a process called shot blasting. This cleans the casting, revealing the rough engine block. To relieve internal stresses caused by the cooling process, the block is then heated to 1,100 degrees Fahrenheit, preventing future cracks. Finally, the block undergoes a machining process called debarking, which removes rough surfaces and ensures the block's uniformity and structural integrity before it moves on to the final machining stage. Caterpillar's Mach Marine Engine Manufacturing Facility in Kiel, Germany, is a hub of world-class engineering and precision manufacturing. One of the critical processes at the Kiel facility is rod boring and testing. This involves the precise machining of connecting rods, a crucial component of marine engines. The accuracy of this process ensures that each connecting rod can withstand the immense stresses it will encounter in operation. Another advanced process employed at the Kiel plant is plasma valve machining. This technique involves using plasma technology to machine valve seats and guides with exceptional precision. The plasma process enhances the durability and longevity of these components, which are subjected to high temperatures and pressures in an operating engine. Cylinder head machining is another vital process in the production of Mach marine engines. The cylinder head is a complex component that requires meticulous attention to detail during manufacturing. At the Kiel facility, advanced machining techniques are used to ensure that each cylinder head meets the exacting standards required for marine applications. This precision is critical to the overall performance and efficiency of the engine. The assembly hall at the Kiel plant is where the various components of the Mach marine engines come together. This stage of production involves the final installation of components, ensuring that every part fits perfectly and functions as intended. The assembly process is highly coordinated, with a focus on quality control at every step. Renowned for producing high-performance marine engines, the Kiel plant is a cornerstone of Caterpillar's global marine operations, combining cutting-edge technology with decades of expertise in marine engine production. Research and development, R&D, is another key aspect of Caterpillar's operations in Kiel. The R&D team works continuously to improve engine performance, efficiency, and emission standards, keeping Caterpillar at the forefront of marine engine technology. Before leaving the Kiel plant, every engine undergoes on-site testing to ensure it meets Caterpillar's stringent quality and performance standards. These tests simulate real-world operating conditions, ensuring that each engine is ready to perform reliably in even the most demanding marine environments. Modern technology plays a crucial role in the development of marine engines, exemplified by the WinGD-XDF engine. From concept to reality, the first low-speed, low-pressure X62DF engine was engineered specifically for large LNG carriers. This cutting-edge engine combines advanced fuel injection systems, electronic control units, and precision manufacturing techniques to meet stringent emissions regulations while maintaining high efficiency and reliability. The XDF technology is designed to be compliant with IMO's Tier 3 NOx and SOx regulations, providing a sustainable and powerful solution for the marine industry. Japan Engine Corporation is at the forefront of marine engine technology, specializing in the assembly of state-of-the-art diesel engines. One such example is their latest 5-cylinder engine with a bore size of 500 mm and a piston stroke of 2,300 mm, capable of producing 1,780 kilowatts per cylinder. The assembly process of this engine involves several high-precision steps. Components are first meticulously machined and inspected to ensure compliance with exacting standards. The cylinder block, crankshaft, and pistons are then assembled with extreme care to maintain tight tolerances. Advanced techniques are employed to ensure that the engine's moving parts work in perfect harmony, reducing friction and wear. This engine is a testament to the integration of advanced engineering and environmental compliance, meeting the 2020 SOx emission regulations, Tier 2, Tier 3 NOx regulations, and the Energy Efficiency Design Index requirements. The engine's design also incorporates innovations that contribute to a simplified engine room arrangement. Notably, the reduction and miniaturization of the SOx scrubber and heating equipment allow for a more compact and efficient layout. This not only saves space but also reduces installation and maintenance costs. The focus on reducing the specific fuel oil consumption further enhances the engine's efficiency, making it a cost-effective and environmentally friendly choice for modern vessels. The engine generator sets used in village power plants are powered by heavy-duty, medium-speed, 4-stroke reciprocating engines. These sets consist of an engine directly connected to a generator through a flexible coupling. Both the generator and the engine are securely mounted on a shared base frame, which is supported by steel springs on the concrete foundation. The engines feature turbochargers and charge air cooling systems. The turbochargers function to increase the pressure in the charge air receiver and are powered by the exhaust gases from the cylinders. Each cylinder head is equipped with 2 intake air valves and 2 exhaust gas valves, all operated by a camshaft. In liquid fuel engines, the camshaft also controls the fuel oil injection pump. Decades of intensive research and development, along with millions of operating hours in various demanding continuous duty applications, have proven that Vela medium-speed 4-stroke engines are the best in the market. The V6 engine block casting process is a highly intricate procedure that involves several stages, from preparing the cores to the final casting. The following outlines the major steps in the manufacturing process. The process begins with the creation of hot box pre-coated sand cores. These cores are essential components that form the internal cavities of the engine block, such as the coolant passages and oil galleries. The hot box method involves using sand pre-coated with a resin that, when heated, cures and hardens, forming the core. The sand and resin mixture is blown into a heated core box, where the heat activates the resin, causing the sand grains to bind together, making cold box sand cores with sand and resins. In addition to hot box cores, cold box sand cores are also used in the casting process. Cold box cores are made using a mixture of sand and resin, but unlike the hot box method, these cores are cured at room temperature. The sand and resin mixture is blown into a core box, where a catalyst gas is injected, causing the resin to harden and bind the sand grains together. This method allows for more precise and complex core shapes, which are essential for creating intricate passages within the engine block. Once the cold box cores are formed, they are removed from the core box and prepared for the next stage. Dip coating and drying sand cores. After the sand cores are created, they undergo a dip coating process. This involves immersing the cores in a refractory coating, which helps to protect the core from the molten metal during casting. The coating also aids in achieving a smoother surface finish on the final engine block. Once coated, the cores are dried in a controlled environment to remove any moisture and ensure that the coating is properly cured. This step is crucial, as any residual moisture can lead to defects in the casting process. Installing heated liners and making up sand cores to positions. The next step involves the installation of heated liners within the sand cores. These liners are typically made of iron or steel and are used to reinforce critical areas of the engine block, such as the cylinder bores. The liners are preheated to a specific temperature before being inserted into the sand cores. This ensures that the liners remain securely in place during casting and helps prevent thermal shock when the molten metal is poured. Once the liners are installed, the sand cores are assembled into their final positions within the mold. This assembly process requires precision, as the placement of the cores directly affects the internal geometry of the engine block. Low-pressure casting. With the sand cores and liners in place, the mold is ready for casting. The V6 engine block is typically cast using a low-pressure casting method. In this process, molten aluminum or other suitable metal alloys are poured into the mold under low pressure. The low-pressure technique allows for a controlled flow of metal, reducing turbulence and the likelihood of defects such as porosity or inclusions. The molten metal fills the mold cavity, surrounding the sand cores and liners, and begins to solidify. The low pressure ensures that the metal completely fills the mold, resulting in a dense, high-quality casting. Once the mold is filled, it is left to cool and solidify. This cooling period typically lasts about 10 minutes, depending on the size of the casting and the material used. During this time, the molten metal fully hardens, taking on the shape of the mold and the internal features formed by the sand cores. Engine repair and overhaul are crucial aspects of vehicle maintenance, ensuring that engines perform optimally and last as long as possible. Among the most significant and complex tasks in this domain is the engine block replacement. This process is essential when the engine block, the core structure of the engine, suffers irreparable damage due to wear, overheating, or other mechanical failures. This guide provides a detailed explanation of engine repair and overhaul, with a specific focus on engine block replacement, including relevant technical details and numeric specifications. The engine block, also known as the cylinder block, is the main structure of an engine. It houses the cylinders, pistons, crankshaft, and other essential components. Typically made from cast iron or aluminum, the engine block's integrity is critical to the engine's overall functionality. A damaged engine block can lead to severe performance issues, including loss of power, overheating, and even complete engine failure. Common reasons for engine block replacement include cracks. These can occur due to overheating, freezing, or high stress conditions. Even small cracks can lead to significant coolant or oil leaks, compromising engine performance. Worn cylinder walls. Over time, the cylinder walls can wear out, causing loss of compression and power. While minor wear can be addressed through reboring, severe cases may necessitate block replacement. Severe corrosion. Corrosion can eat away at the metal, leading to weakened structural integrity and potential failure. Before delving into engine block replacement, it's essential to understand the broader context of an engine overhaul. An engine overhaul typically involves disassembling the engine, inspecting all components, and replacing or refurbishing worn-out parts. The steps include disassembly. The engine is removed from the vehicle, and all its components are disassembled. This includes removing the cylinder head, pistons, crankshaft, and other accessories. Cleaning and inspection. All parts are thoroughly cleaned, and critical components like the cylinder head, camshaft, and pistons are inspected for wear or damage. Non-destructive testing methods, such as dye-penetrant inspection, might be used to detect cracks in the engine block or cylinder head. Replacement of worn parts. Parts like piston rings, bearings, and gaskets are replaced as needed. If the cylinder walls are worn, they may be rebored or sleeved. Reassembly. The engine is reassembled with all the new or refurbished parts, ensuring that everything is torqued to the manufacturer's specifications. Testing. After reassembly, the engine is tested to ensure it operates correctly and meets performance standards. Engine block replacement. A step-by-step process when an engine block is determined to be beyond repair, it must be replaced. Here's a detailed breakdown of the engine block replacement process. Engine removal and disassembly. The engine is removed from the vehicle using a hoist. The engine is disassembled, and all components attached to the engine block, such as the cylinder head, oil pan, and timing chain, are removed. The engine block is then separated from the transmission. Preparing the new engine block. The replacement engine block must match the original in terms of specifications and compatibility with the existing components. Before installation, the new block is inspected for any manufacturing defects or damage. Measurements, such as bore diameter and deck height, are taken to ensure they meet OEM, original equipment manufacturer, specifications. If necessary, the new block is honed or bored to achieve the correct cylinder size. Transferring components. Internal components, such as the crankshaft, pistons, and connecting rods, are transferred from the old block to the new one. All components are inspected and refurbished as needed. For example, the crankshaft journals are measured and polished to ensure they are within tolerance. The cylinder head is also reconditioned, and new head gaskets are installed. Reassembly. The engine block is reassembled with the transferred and new components. Critical torque specifications are followed for all bolts, particularly those on the cylinder head and main bearing caps. The timing chain or belt is installed, ensuring correct alignment with the camshaft and crankshaft. Engine installation. The reassembled engine is installed back into the vehicle. All connections, including electrical wiring, fuel lines, and cooling hoses, are reattached. Initial startup and testing. The engine is filled with oil and coolant, and all systems are checked for leaks. The engine is started and run at low RPM to allow the new components to bed in. Performance tests, such as compression checks and oil pressure tests, are conducted to ensure everything is functioning correctly. The water injection system in UE engines enhances fuel economy and reduces NOx emissions by injecting a fine spray of water into the combustion chamber along with the fuel. The system works by using both engine-driven and electric-driven pumps to pressurize water, which is then injected in stratified layers with the fuel. This process occurs through a single fuel valve that delivers the fuel-water mixture into the combustion chamber in multiple layers. The water cools the combustion temperature, leading to more efficient fuel burning and a significant reduction in NOx emissions. The system integrates with various components, including the exhaust valve actuator and fuel pump hydraulic oil system, to ensure precise timing and optimal performance. This cutting-edge technology represents a significant advancement in achieving higher fuel efficiency while meeting stringent emission standards. The trial run of a marine diesel engine, such as the 6U Eco, is a crucial procedure conducted at the shop to ensure the engine's performance and reliability before it is installed on a vessel. This engine, with 6 cylinders and a 350mm cylinder bore, is designed to develop 4,000 kilowatts at 127 revolutions per minute, making it a powerful prime mover for a bulk carrier constructed at a Japanese shipyard. The trial run, which spans nearly 4 hours, begins with an air run to check the engine's basic functionality without fuel injection. Once the engine is started, the load is gradually increased, beginning with a 25% load. During this phase, various measurements and adjustments are made to ensure that the engine operates smoothly under partial load conditions. After this, the load is increased to 50%, followed by further increments to 75% and finally 100%. At each stage, the engine's performance is carefully monitored, and necessary tunings are applied to optimize its operation. The goal is to ensure that the engine can handle full load conditions effectively, providing consistent power output and efficiency. Once the engine has successfully operated at 100% load, the load is gradually reduced, and the engine is shut down, marking the end of the trial. This rigorous testing process ensures that the engine will perform reliably when installed on the ship.